So we did wonder whether that problem is because the dendritic cells are having trouble moving from the lung to the lymph node. So one way to look at that, in sort of a different experiment, a little bit easier to do because it doesn't involve TB, is to put LPS, lipopolysaccharide, down the airway of the mouse. That will activate lung-resident dendritic cells to move to the lymph node. So we put down into the trachea of our volunteers far red, a fluorescent dye that labels the leukocytes in the airways, and LPS to promote dendritic cell maturation and trafficking to the lymph node. About 0.5 to 1% of the cells that we can lavage from the airway of a healthy mouse are dendritic cells. There are many more parenchymal dendritic cells, but the ones that are in the airway, accessible to our far red dye, about 0.5%. But that's enough to easily be able to track, and this is just showing, so we harvested their lymph nodes about 20 hours after we stimulated and labeled them, and then we could track the far red positive cells moving into from the lymph nodes. So we harvested the lymph nodes, we look at the far red, we can see positive cells, and then gating on the far red positive cells, we can use CD11C and CD11B to identify a dendritic cell population, because some of the labeled cells will be macrophages that are probably not important for priming in a naive mouse. And when we look at these CD11C and CD11B positive dendritic cells that are far red positive, that come from the lung, and we look for co-stimulatory molecules, we see that they have equal expression of CD40, more or less, equal expression of MHC class II, and equal expression of CD80 and CD86. So no evidence in this model, it's not exactly TB, but at least diabetes does not interfere with the ability of dendritic cells to traffic from the lung to the lymph node or to express the co-stimulatory molecules. And in other experiments I won't show you, we also see no problems with antigen processing and the presentation of peptides. So again, it's kind of confusing. We have this delay in getting priming going. We can see there's a delay in the antigen getting to the lymph node, but there doesn't seem to be any problem with the trafficking of these dendritic cells to the lymph node. So again, I kind of scratched my head and I went back and looked at some of the early data. And I went back and looked at the lung sections of lesions. So these are non-diabetic mice here. These are the diabetic mice here. On the top, this is at the 2-week time point, and the bottom, this is at 28 days, 4 weeks. And for the most part, it's very hard to see any lesions in any of these mice, but if you look closely, you can see small lesions forming in the control mice, the non-diabetic mice. And we didn't see these in the diabetic mice at this time point. There weren't very many of these lesions, but we could see them in the controls. In the diabetic mice, we could see really none. Later, they have equal number and size of lesions, and that's at 4 weeks. Beyond that, the diabetic mice actually have much more lesions and a bigger size, mostly just bigger. So we went back and did immunohistochemistry to see if we could see where in the lung the bacteria were. So here we're doing immunostaining with an anti-PPD antibody that works well on formalin-fixed paraffin sections. On the top are some sections from control mice, on the bottom diabetic mice. Again, this is day 15, essentially 2 weeks after infection. And in the non-diabetic mouse, we can see those little tiny lesions that we can see at 200 magnification. Here at 400 magnification are seen to be aggregates of myeloid cells, almost no lymphocytes, a few neutrophils, mostly myeloid cells that are probably largely macrophages, but also some dendritic cells. And they're surrounding macrophages that are infected with TB. In the diabetic mouse, at this time point, we couldn't really see lesions, but when we stained with anti-PPD and looked at high power, we could in fact see that there were foci of infection. And what we had was infected macrophages sitting in the alveolar compartment with almost no or no recruited myeloid cells in their vicinity. So this, I think, is a real clue as to sort of where the problem lies. It's not in the dendritic cell carrying antigen from the lung to the lymph node. I believe it's in the dendritic cell arriving at the site of infection to acquire antigen. So to sort of summarize this part, and I'm trying to go over time, because I like to talk. First of all, what we saw was that there is TB susceptibility in the diabetes. So we think we have a model that could reflect the human condition. And interestingly, it is seen only in mice with chronic hyperglycemia, which to me is comforting because I think that that is consistent with other types of diabetic complications. And the degree of this immune deficiency is not terribly severe. And that's also comforting in terms of the model, because humans with diabetes are more susceptible to TB. They have worse TB, but the relative risk is nowhere near that you would see with HIV/AIDS or with silicosis or other really strong risk factors. So I think that that's pretty comforting that the model may be worth continuing to pursue. What we found was a delayed expression of the adaptive immune response, which is the only immune response that can control TB. We see that the mice, when they do, the diabetic mice, when they finally make an immune response, they make an exaggerated immune response. That may be because by the time it gets mounted, they have 10 times more antigen. I think that's very likely. But I think something that we might want to investigate in the future is whether there are also some failure of the diabetic host to limit the inflammation. And the inflammation, the immune inflammation in TB, is the disease. The bacteria don't make toxins, they don't destroy tissue, except in rare cases of completely immunosuppressed people. They don't produce anything that looks like septic shock. What kills you when you have tuberculosis is your immune response, which eventually destroys your lungs. So we found that there was this late delivery of the antigen to the lymph nodes, and probably no defect in dendritic cell trafficking from the lung to the lymph node, but rather some defect in recruiting the myeloid response to the site of infection, where alveolar macrophages are initially infected. And so this then kind of leads to where our work is going now in the future, which is there are two simple explanations for this. Either the infected macrophages are not making signals necessary to recruit the inflammatory response. Something about diabetes is causing an inhibition of their ability to produce those cytokine signals. Or alternatively, maybe they make a good signal, but there is some barrier imposed by diabetes to the responding cells. And I actually favor the barrier hypothesis, but I have no data for that yet. And my postdoc, Therese, likes the weak signal hypothesis, so she does the experiments she wants, and so I have a little bit of data on weak signal. So just looking at what we were looking for are low levels of chemokines involved in dendritic cell recruitment. And if you take whole lung homogenates 2 weeks after infection, the diabetic mice may have less identifiable CCL2 or CCL5 protein. So these are two chemokines that are described in the literature as involved in the recruitment of naive immature dendritic cells. The problem with the interpretation of the experiment is that these mice also have, the control mice that have more of these chemokines, have inflammatory lesions in their lungs. They have a lot of myeloid cells there. And those myeloid cells could conceivably be the cells making the chemokines that we're measuring. So I don't know at this point whether this small difference is a cause or an effect of the late recruitment to the diabetic mouse. We're beginning to do some in vitro experiments. I kind of favor working with these kind of disease models as much as possible in vivo. Because it's very difficult, very easy to get led down pathways that are non-productive with artifacts of in vitro experimentation. Having said that, we do plenty of in vitro work in my lab. So what we're doing here is kind of a mixture. We have made Therese. I shouldn't say we, because I sit in the office and go on the internet, and people in the lab go in the lab and do the work. So Therese made mice diabetic. She waited till they had chronic diabetes, and then she did lavaged out macrophages, and challenged them with TB ex vivo. So the macrophages have spent a minimal amount of time outside the diabetic environment. And the tissue culture media that we're using is RPMI 1640. I don't know if any of you do cell culture and work with RPMI 1640, but RPMI 1640 is essentially diabetes in a bottle. The glucose level of that culture media, and of most culture media, would be at a level that would be considered very severe in a person with diabetes. I forgot in millimoles, but at 450 micrograms per deciliter. So at least when we're taking these cells out of the diabetic mice, they're not now going into a low glucose media. They're seeing a glucose concentration that they're used to. And so she's been looking at sort of simple macrophage functions. This is phagocytosis. We're looking at phagocytosis of a red fluorescent strain of TB, H37RV, and cherry. And you can see by fluorescence microscopy, both the non-diabetic and the diabetic macrophages can ingest TB. I think she selected these pictures because they give a hint that the diabetic mouse has a phagocytic defect. I'm not convinced. This is all really pilot data from now on, so very small numbers, and I think none of these things can be taken as hard and fast evidence. But by microscopy, she has a suggestion when she's counting cells, looking at the percent of phagocytic cells, that is, counting 100 cells, how many have any bacteria in them. There might be a slight defect in the diabetic mouse, at least at this early time point. She's also done this by flow cytometry, so you can see the M-cherry staining here. One of the problems that my lab deals with a lot in flow cytometry of lung leukocytes is autofluorescence. So the people in the lab, I think, have been pretty good at understanding autofluorescence. This tail here is the autofluorescence of macrophages, which is mostly green but bleeds into other wavelengths. So here, just gating on the M-cherry population, we can see that there is a lower mean fluorescence intensity in the diabetic macrophages. And if you look at this M-cherry population, there appears to be kind of a high and a low M-cherry, and the high M-cherry high cells are much more common in the non-diabetic mouse than the diabetic. So that's a little bit of weak evidence that there could be some problem with the basal state of the macrophage in the diabetic lung. Now, I don't think that these macrophages are able to phagocytose. We clearly see that they can. We can clearly see that the macrophages have ingested TB in the mouse in vivo after an aerosol infection. So I don't think that the problem is a failure to phagocytose TB. And in fact, if you deplete alveolar macrophages in a mouse and then challenge with TB, the mice are protected, because the TB needs the intracellular niche for multiplication. What I think this could suggest, though, is that there is something different about the biology of the macrophage in the diabetic environment that may influence its ability later to recruit non-infected cells to the site of infection. She's also looked a little bit at cytokine production in these cells, re-stimulated ex vivo, and again, maybe there are some small differences, but these are relatively large amounts of CCL5 and huge amounts of IL-6 being produced. And whether there's a biological significance to this, potentially, we can't even really do statistics on these yet, but if these trends hold up, they're likely to be statistically significantly different. Whether they're biologically significant remains to be seen. But again, further evidence that there may be reduced phagocytic and phagocytosis and cytokine production in the diabetic macrophages, suggesting maybe an altered functional state for these macrophages, and that could support the weak signal hypothesis. So, how could an alveolar macrophage be impacted by diabetes? As I'll just mention briefly now, and I'll mention again at the end, there are sort of known biochemical pathways for complications in diabetes.